Good morning, everyone, and welcome to this live talk on wireless communication systems design with MATLAB and Simulink. My name is Abdurrahim Balaisawi, and I'm a senior application engineer, part of the technical team here at CS. I have background in radar, communication, signal processing, and artificial intelligence for these applications. At CS, the exclusive partner of Matchbox in the Middle East, I focus on radar and communication areas and application, and I'm excited to take you today through this session on wireless communication system design. Here is a quick look at our agenda for today's session. We will start with a brief introduction. Then we will dive into wireless standards modeling to understand how protocols are represented in simulation. From there, we will look at front end and antenna design, followed by end-to-end simulation to see the full communication chain and link and system level in action. Next, we will explore wireless scenarios modeling, where we simulate wireless communication systems in 2D and 3D scenarios. Then we will shift to development and deployment of this wireless system to hardware, bridging the gap between simulation and implementation. And finally, we will wrap up with a summary and call to action to help you take the next steps. Begin with a quick introduction to set the stage for what we are exploring today. We are seeing explosive demand across different industries when it comes to wireless communication standards, from consumer electronics to automotive and IoT, each with unique requirements. These standards are powerful, but implementing them involves a lot of sophisticated features, including massive MIMO, beamforming, and so on and so forth. There is also a constant pressure to push more data through limited spectrum. Here we are talking about the increase in the rate or the data rate, which means tighter requirements on modulation, coding, system performance, and other chain or wireless chain components. Traditional design silos are no longer sufficient for for designing and deploying such systems, such complex systems. System level performance also depend on a seamless integration between different components, including the digital RF and antenna systems. So MATLAB and Simulink, alongside with other wireless toolboxes, help you overcoming these challenges. We have a set of toolboxes. Each is dedicated for a specific part of this workflow. Here I mean the wireless communication system design workflow. Depending on what you or your team is trying to do, teams using various combination of Matchbox wireless products that support their end-to-end simulations design workflow. Whether you are modeling a commercial standard or performing end-to-end simulations, or modeling scenarios and performing system-level simulations. Also modeling the behavior. Here we are talking about the front end and the antenna modeling. You have a set of the toolboxes, capabilities like that are shipped with these toolboxes that help you with implementing the RF and the antenna behavior, or even testing and deployment to hardware. Let's start by looking at how we model wireless standards like satellite communications systems, 5G, or even Wi-Fi 7 using Matchbox tools as the foundation for the system design. Here we discuss different technologies and standards that enable wireless connectivity to internet. Wherever you are, or whenever you are trying to connect this to your users. At the largest scale, the emerging technology like satellite communication allows this communication or this networking over satellite communication. Cellular networks have been connecting our phone and mobile devices to the internet wherever there is a base station coverage available right now. 5G or the wide area networks are expanding in the world, providing higher throughput and capacity. And we are not only talking about 5G, we are now talking about the 5G advanced and 6G, which is coming soon. We have been using Wi-Fi local area as well to connect with other people, other users, through what we call the local area network. And at a small scale, or in the for short ranging, we have been using Bluetooth to send data over this Bluetooth technology. So there are many standards, and so we have different toolboxes for that. First, let's start with this Bluetooth technology. Bluetooth design challenges are far-ranging. I mean, there are so many, and they can be categorized into three groups. Those that are related to the Bluetooth or the low-energy Bluetooth transceiver chips, and the others that are related to the coexistence of these Bluetooth devices alongside with some other wireless technologies like Wi-Fi or 5G. Another type of challenges that Bluetooth designers are facing is to use the Bluetooth at a bigger system, using it for localization or for estimation of audio latencies. The Bluetooth toolbox or the MATLAB Bluetooth toolbox help you with overcoming these challenges by offering a set of capabilities, including waveform generation and end-to-end link simulations, signal recovery and analysis, Bluetooth and WLAN coexistence, and then many examples and features available under these toolboxes that allow the localization based on Bluetooth technology. Or even you can add more degree of freedom into your simulation by integrating by modeling and integrating the network layer. This toolbox has many benefits, including standard-based functions and examples supporting the latest releases. So MathWorks development team is continuously adding more features to support the latest releases of different wireless technologies. It also has reference receiver designs. It can be used for modeling the physical layer, the link layer. And one of the greatest features that are available in these toolboxes is the access to the MATLAB source code itself for, customization and automation. And another nice feature, which is the extensive documentation that explains not only the functions and the blocks, but also the example sheet with the toolbox. If you wish to share your work or your Bluetooth application with people they don't have, or with your team workers that they don't have a license for this toolbox, you can generate an app and share it with them. Now talking about WLAN or Wi-Fi. So this toolbox is also for modeling the physical layer and the MAC layer of the WLAN systems. And when we say that, we are here talking about two parts or two components, the physical layer, including the transmission, propagation channel, receiver, and so on and so forth. And then you can perform some sort of simulation at this level, or what we call the link level. Moving forward, you would like to model the MAC and the MAC layer and include it or simulate it alongside with the physical layer. This supports the two links, the downlink and uplink. The WLAN toolbox is implementation of the standards, the known standards that we have listed in this table. So it supports different standards from the legacy one, which was released a long time ago, to the latest one, which we are trying to implement, which is the Wi-Fi 7. Some of the use cases or the benefits of using WLAN toolbox are many. I'm including some of them here. The signal generation and analysis using interactive tools such as the waveform generator or the wireless waveform generator app. Then you have this waveform, you can include it, or you can build on the top of it to perform end-to-end simulation, where you can include also your RF impairment, the channel impairment, and so on and so forth. If you would like to do some measurements and tests, you can connect this toolbox to the hardware and acquire data and perform these measurements. Or you can use it for you can use it alongside with some radio hardware for signal detection and analysis in MATLAB. The toolbox or this WLAN toolbox support connectivity to RF hardware and SDRs. So you can do, or you can perform over-the-air testing, or you can test with MATLAB and this RF hardware. Another feature that has been added recently is the system level simulation, where you can involve or include the different other layers alongside with the physical layer and perform a sort of system level simulation where you can assess the transmission of the data in a better manner. Now talking about the LTE and what we built on the top of this LTE. LTE or 4G as it is known is implemented in MATLAB using this LTE toolbox that allows you to simulate, analyze, and test the physical layer of LTE and LTE advanced wireless communication system. The toolbox, same as the other toolboxes, has many use cases and applications alongside with some examples or golden examples. So you can generate standard-based waveforms or LTE standard-based waveforms interactively using the wireless waveform generator. And then using that, you can analyze the spectrum, or you can also visualize this data in a kind of spectrogram. Okay. The other application is end-to-end simulations, where you perform this link or this LTE link simulation at the link level. This will allow you to evaluate the transmission or the communication success. So you can look at the throughput against the SNR, or you can just like assess your communication using the bit error rate. The other feature that allows you, this toolbox allows you to do is the test and measurements. And of course, you can connect to hardware and perform signal recovery, spectrum monitoring, and so on and so forth. The tool or the toolbox also connects with hardware, including the SDRs and RF hardware. Now let's talk about the technology that was built on the top of LTE. So many features were, let's say, cloned from LTE to build the 5G technology. And 5G toolbox is the MathWorks toolbox that allow you to model, design, simulate these 5G systems in a software, in a sort of digital manner. Okay. The toolbox has a couple of application and use cases, including the waveform generation, the end-to-end simulations, the measurements, where you can assess the performance of your communication or end-to-end simulations, and also has features for signal detection, and most importantly, it connects to the hardware as well. The toolbox has a lot of various benefits and case studies or case uses. Here I'm talking about the benefits. So the functions and examples are 5G specific or 5G based standards. It has also an extensive documentation. These extensive documentation or these examples and functions are verified against external sources. And then you have the access to the full MATLAB source code. One more thing that I would like to highlight here is that the 5G toolbox development team at MathWorks is adding more features to support the 3GPP latest release. A lot of people now are not talking about 5G. They started already talking about designing the next technology, which is 6G. 6G exploration library, a free package shipped by MathWorks, allows you to explore, model, and test candidate 6G waveforms and technologies. So this 6G library, which is again a free, library to download and install and use, has a lot of features, including the waveform exploration, managing large and long-running simulation. It has also some features for AI for wireless, so that you can develop on the top of 5G and get something close to 6G. And it also has propagation losses and channel model, RF components modeling, and so on and so forth. This is an active area of development, of course, and so we are we encourage people to reach out to us if they need features for their work, and we would like to do the same with you. So if you have something related to 6G that you would like to see in 5G toolbox or this library, please reach out to us and we will be more than happy to connect and see how we can support. Talking now about the SATCOM design. So same for the other wireless standards, the SATCOM design has many challenges. It can be also categorized into 3 groups. The first is the coverage. One of the challenges is the coverage. We need to have a coverage for different orbits. Also, when we have challenges related to visibility and link analysis. The other challenges are also are related to the transmitted output power, the link budget sensitivity analysis, and the selection of the modulation and coding schemes. Also, some of the challenges are related not only to the SATCOM itself, but they are related to satellite-based channel model, the implementation of standard-based SATCOM systems, and so on and so forth. Adding on the top of that, so many SATCOM standards, there are many SATCOM standards. This can be seen as a challenge. And when we say many SATCOM standards, we have standards for broadcasting, some others are for cellular communication, and other challenges, or a challenge which is related to mainly SATCOM standards is related to satellites, command and control, and lastly, the optical communication, which was added also to the set of standards that SATCOM should support. The satellite communication toolbox addresses these challenges and more. So it works with other toolboxes, such as communication toolbox, to perform the orbit propagation and visualization and access to the link analysis. It also allows link budget analysis if you are at the early stage of your SATCOM design, so you can perform this link budget analysis. Or you can generate standard-based waveforms by using interactive tools that are shipped with this toolbox. And one of the most important the features available in this toolbox is the end-to-end simulations to assess the performance, where you can include the timing, the frame synchronization, optical links, and so on and so forth. And then here we are talking about a performance assessment at the system level. The satellite communication toolbox has so many benefits, including standard-based functions and examples, interactive link budget apps to perform the link budget analysis, so many reference receiver designs. When we say designs, we mean here MATLAB codes and Simulink models, extensive documentation, and of course the access to all this documentation alongside with the MATLAB code. And it has support for code generation. If you would like to take your SATCOM algorithms to deployments, you can generate code from and deploy to the hardware. Let's now talk about how to add more fidelity into our SATCOM or wireless design. With the physical layer model, the next focus is on designing, simulating, and integrating RF front end and antenna system into link level model, so that we improve the fidelity of our wireless design. Challenges in wireless in RF wireless systems modeling are quite so many, and the main challenge here is the multi-domain modeling. When we say multi-domain modeling, we are talking about antennas, we are talking about RF front end, we are talking about the fixed or the mixed signal, and we should not forget the DSP algorithms that should be also tested with this front end and antennas. MATLAB and Simulink enable the addition of the desired fidelity to your physical layer model by offering or by allowing you to design the front end that will include the noise budget, the gain, the nonlinearity, the text linearization, and so on and so forth, or by also modeling and integrating antennas that can be array or array signal processing like beamforming. You can also include the propagation effects and the channel effects on your signals. And let's now talk a bit about this array signal processing and how we can support them. When a system is equipped with an array of antennas, it opens a whole new space. And that's called a spatial space, and for us to explore and take advantage of. So using an array instead of an element or an antenna element open another door for us. And that door is the estimation of the direction of signals coming to our receiver, or also we can steer the beam using the beamformers that we have implemented in the MATLAB and Simulink. Designing arrays is also challenging, and we need some sort of interactive tools to do that. MATLAB has this sensor array analyzer app that allows you to design and analyze these arrays. And the workflow is simple. You define and analyze arrays, then you define the custom antenna elements, you import the antennas, you calculate the beam steering, and you generate a MATLAB script. So the workflow for this app, as so many MATLAB apps, it starts from the left to the right. You perform the analysis, then you export to MATLAB for further automation. So many other features are included into Antenna Toolbox to support the antenna array design and analysis. And not only that, Antenna Toolbox has other features, including the built-in elements or antenna elements, different solvers that help with installation of antennas. Also, it helps with optimizing your antennas to meet the performance. And you can move from antenna to fabrication by importing or exporting from other or external tools. And one of the other features is to generate scripts to MATLAB or generate blocks to integrate with Simulink. Another feature is the error propagation modeling and simulation over maps. You can use your own digital terrain data and perform the analysis of propagation over that terrain. The Antenna Toolbox has a couple of apps, including the Antenna Designer that allows you to design and simulate antenna, analyze that, you can look at the pattern or the pattern diagram in 2D, 3D. And also it helps with visualizing or overlaying the antenna alongside with the 3D pattern. But before that, it has or it gives you the possibility to adjust your parameters to meet your requirements. And as for many other apps, you can generate a script or export as a system object or as an object to MATLAB and use it or integrate it with your MATLAB code or Simulink designs. And to design now the array or the antenna array, you can use the Antenna Array Designer app, where you can include the antenna element you designed using the Antenna Designer into this app and use it for building an array and analyzing it. So the analysis that we usually do, we do the coupling analysis between adjacent antennas or antenna elements. We understand what is the effects of one on the other, and so on and so forth. We can also use different antenna elements. We can add the backend structure to improve the antenna performance and get something close to reality. And we then can start the analysis. We can analyze it by looking at the S parameters, including the reflection coefficient or and the transmission losses and so on and so forth. Later on, you can generate a script or export as a MATLAB variable. How to get started with Antenna Toolbox? There are so many examples shipped with this toolbox, and they cover different areas, from importing from third-party tools to MATLAB, to designing specific antenna for radar or wireless communication, to designing and testing antenna over terrain. So I would recommend that you explore these examples after this session. Now let's talk about front-end, the RF front-end, how MathWorks tools can help you with that. RF modeling is a trade-off, is always a trade-off, and it's useful for adding more fidelity into your system models. We learned before that with these standards, with communication toolbox and wireless standards toolboxes, you can design the baseband or the physical layer. Now we would like to add or improve the fidelity of that model by integrating the circuit envelope. This circuit envelope can be designed, or these circuits can be designed and analyzed using different interactive apps that are shipped with RF toolboxes, RF block sets, and antenna toolbox. And they allow you to perform the design, to perform this analysis by looking at the nonlinearities, looking at the power, and that can be done by interactively using an app called RF Budget Analyzer app, which helps with performing the freeze analysis, the harmonic balance analysis, and also it helps with analyzing it by visualizing the S parameters, the losses, and so on and so forth. And also it has the exporting features to MATLAB and Simulink. The app is fully interactive, and it helps also with understanding the RF front-end design. So as I said, the last step in each of this application is to export, so that you integrate with the physical layer or the baseband components. You can export to RF block set from within this app by just clicking on this RF block set, so that you export to the RF block set. That will create a Simulink model for the RF chain, for your RF chain, and that can be later on integrated with the digital baseband. So the other question that many might ask is, can I do this in MATLAB? The answer is yes. So in the latest release, MathWorks added an object called RF system that helps with performing circuit envelope simulation of RF systems in MATLAB. And what you see here is the object, which requires performing the RF budget using the app and then passing to it as an input argument. And this code is actually equivalent to this Simulink model. So now that we have learned how to design the digital baseband of these wireless communication systems, and we learned how to improve the fidelity by adding the RF impairments and antenna impairments. To assess the full system behavior, we bring all the components together in end-to-end simulation, and that can be at the level, the link level or system level type of simulation. Let me bring back this MATLAB and Simulink wireless solution and walk you through how they support end-to-end simulations. So, as explained before, there are different solutions for different parts. If you are talking about the generating the waveform, you will need the specific toolbox that generate that specific waveform. Maybe you are designing a waveform for 6G. So in this case, 5G toolbox has an app. It's called 5G wireless generator app. It helps with generating and analyzing 6G waveforms, or candidates at least. And what you see here is the wireless waveform generator that I have been talking about. So with this app, you can generate a wireless waveform for 5G, for LTE, for WLAN, or even for a custom modulation. Here we are generating a downlink FRC, And then we have different parameters, including the frequency range, the MCS, the subcarrier spacing, and so on and so forth. And another tab for the impairments to include the channel impairment and see the impacts on that on the waveform. Later on, you can generate that waveform and start analyzing it using the spectrum analyzer or by looking at the resource grid and the channel view. The last step here is to export to MATLAB as a variable. Another type of simulation is at the link level, and this time we are talking about a 5G NR PD SCH throughput. So we are analyzing this new radio 5G system by looking at the throughput. And this is what we mean by end-to-end simulation. You design or you model the transmitter, you model the channel, and then you model the receiver chain, and you perform the analysis by looking at the throughput or maybe the bit error rate or the block error rate. I'm including here an example for further evaluation of this end-to-end simulation using 5G toolbox. So for SATCOM, we can also do this end-to-end simulation at the link level. We generate a standard-based SATCOM waveform, then we include the RF impairments, and then we model the receiver itself, and we perform different simulation by looking at the synchronized, or by looking at actually at the this is the spectrum analyzer. We just want to understand the attenuation or the losses that happened. And then we can look at the constellation diagram to understand the performance of the receiver. And another way to assess is to plot the timing and carrier synchronization and data that was recovered. These wireless communication systems can be designed in Simulink as well. So where you can in that way you can include also the RF impairments into the receiver and the transmitter. You can generate the digital baseband and get these components together to build your bigger system, which is an end-to-end simulation. And what you see here is a model or a design for MIMO RF receiver with some array signal processing. We are talking here about the beamforming. So the idea is to compare the performance of the receiver without and with beamforming, and this is what we got. So once we applied the beamforming, as you can see, there was an interferer or an interference signal that was filtered out using the beamforming. Okay. Another type of end-to-end simulation is called system-level simulation, where you include the physical layer alongside with the MAC layer, the radio link control layer, and also application layers. For that, MATWORKS has a free or an open source package to model, simulate, and analyze wireless communication networks. It helps you with, improving the fidelity of your wireless communication system level modeling. We then can now place the system into some realistic channel and also some scenarios where we test better and understand how are the performance of our system, and that's called wireless scenario modeling. So we can design an RF propagation scenario, and we visualize it over a terrain. Antenna Toolbox offers a couple of features or a lot of features for visualizing the coverage. When we say that, we mean here the pattern. So instead of visualizing it in 3D, we can visualize it over a map. We can use default medium resolution, or we can import our digital terrain data and use it to model this RF propagation. We can also explore different antenna patterns. We change the antenna design, and we test the communication link and the coverage performance. A simplified workflow for modeling RF propagation starts with creating transmitters and receivers. Then we design the antenna. When we say design the antenna, we can design it interactively using the app that I showed before, or we can write the code if you would like to. Then we start the analysis of the communication link by looking at the coverage and the link, or we can also look at the SNR or the SINR, or another thing is to look at the power itself. So if we are not happy with this coverage, we can use another antenna, or we can steer the antenna so that using beamforming, so we can steer the antenna toward that specific receiver. Here I'm including some RF propagation examples that will help you to get started with using these RF propagation features in your project. So alongside antenna toolbox, we have also features for modeling scenarios for satellite communication systems, and that includes generating orbits in multiple ways. So we generate the orbit, we add the satellite, then we create a ground station, and then we start simulating this end-to-end simulation of SATCOM systems. We can construct a transmitter and receiver. We place the antenna using the antenna toolbox, and then we start the assessment of the communication link and the coverage. You can also perform the steering or the beam steering using an array. So you need first to have an array so that then you can use beamforming to steer it toward a specific ground station, and that will maximize the SNR. So in addition to RF propagation, you can assess the communication link by looking at this reading, the start time, the end time, the duration, and you can also analyze the satellite communication performance by assessing when exactly the ground station can see the satellite and when it's not possible, and that's in 3D type of scenarios, as you can see here. And these are not, plots or shapes, but they are real world shapes that are from the internet. To get started with satellite scenario generation and visualization, I recommend to explore this example, specifically this one, aircraft to satellite communication. So it examines the connectivity of a flight or of a aircraft to a satellite. And there are so many other examples. I include here only 4, but I recommend to check the documentation of satellite communication toolbox to learn more and explore other capabilities. Now that we tested our design in different ways by looking at the performance in end-to-end simulation and the wireless scenario modeling, now we can test with hardware. We can validate further our algorithms by testing with SDRs or testing with the RF hardware like signal generator or signal RF generator and spectrum analyzer. So these are the RF hardware. MATLAB and its wireless add-ons support 2 workflows. So whether you are trying to transmit signals from MATLAB to the specific RF signal generator instrument, that's something possible you can do with MATLAB, and it might require some support packages that are available for you. The other way is to connect an SDR platform to your MATLAB and perform the over-the-air testing. The second part, or the other part, which is at the MATLAB here, is acting as a receiver. So we can acquire signals from RF signal or RF hardware, RF instruments to MATLAB and perform different analysis. The same can be done for SDR. We can connect an SDR receiver to the machine that has MATLAB installed alongside with the other toolboxes and acquire and analyze these waveforms in MATLAB. So there are many supported hardware from different vendors. I listed a few of them here, but you can also do the same with your own hardware. These are some of the supported SDR platforms. Mainly here USRPs. They are quite common in the professional, let's say, market. And there are some other SDRs that you can connect to your machine that has MATLAB and perform, for example, over-the-air testing. Or also you can acquire some data from these SDRs and perform the analysis, the verification of your algorithm, and so on and so forth. The same can be done with signal analyzer, signal generators. I mean here the RF instrument. Using the instrument control toolbox, you can connect or you can establish this connection between this hardware and MATLAB, and I mean visualize your waveforms in spectrum analyzer, or you can connect an SDR to this, or a radio, an RF chain, or an RF circuit to this hardware, to this RF hardware, and then acquire the data in MATLAB and perform different analysis. Here I use case showing MATLAB or the desktop that has MATLAB connected to a spectrum analyzer over these protocols. So the objective is to perform signal acquisition and analysis in MATLAB from a RF instrument. So in MATLAB, you're gonna retrieve the IQ baseband data, and then you can perform the analysis. You can visualize, analyze different measurements that you are interested in. The waveform or the wireless waveform generator has also a feature for transmission. So you don't need to write any line of code. All you need to do is to have the hardware connected to your machine that has MATLAB, and then generate the waveform, analyze it in the software, and go to the second tab. It's called transmitter, and hit this transmit, and then you can transmit your signals over the air. Some of the supported or the vendors that we support are listed here, but this is not an exclusive list of the vendors that we support. The last step in this workflow is to deploy to production. Now we verified our algorithms or our wireless design in the software. We verified it using different levels of modeling. We verified it as well, or we validated it using the RF hardware and the SDRs. Now time to deploy this wireless algorithms to production. And MATLAB and Simulink offers a range of capabilities for that. You can generate a production code, which can be C, C++, or HDL code directly from your MATLAB. You can convert it with few clicks. So we have a tool set that supports or that allows you to generate C, C++ code interactively. Here I'm talking about embedded coder, which can be used to customize the generated code for specific hardware that you are deploying to. And the same applies to HDL coder, where you can optimize the generated HDL. When we say optimization, we are talking about area optimization, we are talking about timing optimization, and so on and so forth, so that you generate a code, an HDL code that can be taken to any simulator, and then you can generate that bit stream and deploy it to your FPGA. The HDL coder is the tool that you need to have so that you can generate synthesizable HDL code from your MATLAB and Simulink designs. And the tool doesn't only generate the code; it helps with the HDL design. So your MATLAB and the Simulink code must be supported for code generation, and HDL coder can help you with that. And then the next step is to generate the code that can be converted from floating to fixed. You can also perform frame to sample, and most importantly, performance and area optimization. And then you can generate the HDL code. You can also generate IP core if you are interested in generating IP core. The deployment is now to convert that HDL code into a bit stream and deploy it to your FPGA. Another workflow that can be one of your interests is to verify that design or that HDL design against the MATLAB and Simulink designs. That's something you can perform also with the supported FPGA. So you can connect your FPGA or the simulator and perform what we call the co-simulation or the co-verification. Here I'm including some of the examples that showcase how to develop and deploy wireless communication systems to production. So I believe we can go to MATLAB. Just want to quickly show you an example here of how an end-to-end simulation looks like. So what I'm going to show in this small example is the design of a end-to-end simulation with RF impairments, and also we're gonna understand how we can correct this impairment. So I have an app which shows this implementation. So if you don't wanna see the code, you can design an app using MATLAB App Designer and add your code as a backend and then perform different type of analysis. The apps can be interactive by setting some parameters. Let me just run this so that I can speak better about this app. So for this QAM with RF impairments example, there are different parameters. I'm talking here about system parameters. And this simulation, by the way, is for a SATCOM design. So the link distance is 35,600, and then we are simulating it in the frequency band C band. We are adding some atmospheric condition. Let's keep it free space for now. The antenna parameters as well are specified here. Next is to add the RF impairments into your design by including the noise temperature and then the high power amplifier backoff. This will tell you about the power below the saturation range, the Doppler error, the amplitude imbalance, and so on and so forth. So these are the different RF parameters that you can tweak or adjust so that you meet the requirements that you are trying to simulate. When it comes to the correction, we can select different ways to correct the impairments, the RF impairments, and the visualization. We can visualize the performance of our end-to-end simulation by looking at the spectra or the spectrum of the transmitter signal, the receiver signal. We can look at the constellation diagram to assess the phase and frequency imbalance, and then we can look at the signal in the frequency domain at the input and the output of HPA or the high power amplifier. To perform a numerical analysis, we can look at the Bayer error rate or the bit error rate. Okay. Next is to just simulate this by clicking simulate. So this is what I'm getting. I'm here like getting a perfect or ideal performance, and the number of errors is 0. The bit error rate is also 0, meaning that I'm recovering the information that I transmitted over this communication system. So I don't see any effects of the RF impairments. To see the effect, maybe we can decrease this power or this backoff, okay, and then resimulate or simulate again the same system. And now we can start seeing few impairments on the received signal. So the received signal is kind of rotated in the constellation diagram, meaning that there is a phase and frequency impairments there. You can keep like playing with these parameters to understand the effects of different RF impairments on your link performance. Or you can also view the code if you would like to, or generate a deployable and production code. And if you wish to stop the simulation, you have also a button for that. Let me just go to the code and show you how it looks like. It's a kind of low code. It's something similar to the object programming type of style. Okay. And so with that, I would like to wrap up, and let's review the workflow. Or let's say, what are the takeaways from this session? So wireless communication system design with MATLAB and Simulink is seamless, easier, and mostly with no code or low code techniques. What you need to do in this case is to focus on understanding specifications and the theory, understanding your algorithms and develop them, test and validate. And MATLAB and Simulink will let you focus on what is critical for your wireless design projects. Here, as a call to action, I'm adding a few features or a few examples that you can explore later on for each of these toolboxes that I spoke about. And there are so many other examples, maybe hundreds of examples shipped with these toolboxes that you can explore to kickstart your projects. And thank you so much. That was the last slide in my presentation.